Hello everybody. Today we have a pretty difficult problem. It's called word search number 2. If you haven't done word search number 1, this will come even more difficult because in word search number 1, you'll be learning how to do backtracking, which is quite necessary for this problem. And this is basically a harder version of word search. So let's take a look at this problem. So given a m times n board of characters and a list of strings, words, return all words on the board. Each word must be constructed from the letter of sequential adjacent cells where adjacent cells are horizontal or vertical neighbors. The same letter cell may not be used more than once in a word. So let's take a look at this board here. So we have a board and we are looking for multiple words. In the original problem, we only had one word that we need to find, and now we have multiple words. This means that after doing our problem, we will need to, if we are able to do this in using the method of what we did before, in word search number 1, we would have to multiply that by the number of words. And that's gonna take a long time because we will have to do n times n, and for each word we have to run DFS for each word length. And so that means this time and space complexity, if we were to do it with this method, it's going to be O of m times n for starts at each position in the board. Like we start here, like at O, and then we have to run DFS for word length. So word length is going to be the length of m times n, as you can see here. 3 times 10 to the 4th power, that's the word length. So times m times n for another, what do you call those things? So it's m times m times n times m times n for the DFS call. And then, we have to for each word. So for each word, that's going to be m times n times o for a number of words, or w for a number of words. W is clearer, and words dot length is 3 times 10 to the 4th. Word length is actually 10. Never mind. My bad. So this length here for the word length is times 10. So I guess that saves it a little bit. Will this time complexity be good enough for us, or would it be better if we did something a little bit better? And that would be like a time complexity where we can save on the output. I mean, save on the words, like how we keep on iterating through the board instead. So this idea instead, what it does is that while there is another word that is possible, we'll continue on the path. So here's what I mean. Let's take a look at another example where this idea might be useful. So here's the idea. We have oat, we have oaks, and we have oath, right? So we should be able to find 4 words. So what happens is that we have to reset every time we find a word, right? And so that's gonna be O of DFS running through every position. And that DFS call is going to be to the fourth power. So it's not actually 10, my bad. So DFS is actually going to be the word length, which is 10. And we're going to do this 10 times. The DFS call, which is to the fourth power. So at each position, we will look at the 4 directions and continue from that point. But on average, that is not the case because not all the directions will continue. We will only continue on one path. So, but that is the worst case, is 10 to the 4th power. Okay, so if we had this, how do we make this faster? Well, one thing we can do for time and space complexity is to use a trinode. So this uses another concept that we may not have learned. It's called a trinode, and a trinode is basically a word which has children, and these children, well, can be, let's say we have oak, O here, and we have a children, we have an A, right? So we have an A, and we have a T, right? We have this T, and now we do a split between oats with an S and with an oaf with a T. So H, oaf. So now let's not play hangman here. Oh, my bad. But this is to demonstrate that there are multiple like branches from this word, from this O. And now, instead of ending our search, as long as there is a word in our path, we will continue searching and seek for, as long as there's a next character is reaching another point in our trinode, then we can continue. And so how does that help us? Is that we no longer have to work for each particular word. We can run through oat, oaks, and oaf all at the same time because, well, we can continue through our trinode. So what type of speed up is that? Like, how much faster are we going? Well, in the worst case, suppose that like we have words that do not share any of the same characters ever, then we still will check items that are in that particular order. And so it'll be the same as this one, I think. Because if all the characters are different, it doesn't matter that we start at the same place, because every time we finish up one word, we would clean it up and would start at the next word. So it will be very similar. But on average, it will be faster. This speed will definitely help us pass these tests. So space-wise, what we need is, well, we need a space to save on our trinode, and our trinode is going to be, like the maximum is number of words. But I don't imagine that we would actually have to save every single word that's completely different, because let's say the length of the word is 10, right? And there's only 26 characters. It's 26 times 10. Now, those are the 26 to the 10th power. Never mind. 26 to the 10th power, because for 26 characters, we can have each branch out into 26 items, and so on and so forth. So it's 26 to the 10th power is our space, specifically. That's the maximum number of space. So this is 26 to the word length. and this is word length to the 4th power for the 4 directions, and we have the number of words here. So with that, I think we are good to go. Sorry, it's 4 to the power to the word length. So that's the amount of variations that we can have. So it's 4 to the word length power. And that's good. That's our time and space complexity. We're 10 minutes in already to understand this problem. And what are some of the edge cases that we can think of? It's that m times n at least have a single item. Like, yeah. So it has to be at least a single item long. So this means that the base case is something like this. So let's eliminate 3 rows, and this is the base case. We have just one I in here. And they're all lowercase numbers, and let's say, what sort of other input can we be limited on? Can we be limited by number of words? How many, can we have infinite number of words, all longer, and they don't start at this board? So that's that. We're gonna output none here. We found the no words in this board here. Perfect. Okay, with that, I think we can get started with our matching, which we talked about earlier already. So our match is going to be a trinode, and it's going to be backtracking, and it's going to be basically a DFS graph type problem. So we have 3 problems in one, and we need a plan for this. So the plan that we have is pretty essential. So create a trinode. The trinode will handle pruning words, so we do not continue seeking the same items. The second plan is that we will create a backtracking on the visited nodes. And 3, we're gonna do a DFS call on all the items with each position in the board. And right, how we're gonna do this DFS call is that we will be calling a DFS on every item. On every item that can be where we can continue on the trinode. Yeah, so that helps a lot. And that's it. I do know for sure that if we tried the other method, where we do not use a trinode, we would fail utterly, and that we would not be able to pass this the submission process. I mean, we can try it and see what happens, but I'm surely it's gonna fail. So we can do it. Let's do it, and I guess that way we can have a part 2 of this video. So let's do a forward in words, and we're gonna do a board. So we're gonna do a 4 length. We need a, oh shoot, what the heck? Okay, so we need length of mn equals length of board and length of board 0 for the columns. So for m, I in range m, and for j in range n, we're going to run a DFS call. And if DFS of this item, which starts at m, I, and j, and the word, we find the word, then we're going to add this word to our results. So results equals empty array, and results dot append word. Otherwise, we'll continue and we'll return the results. So this should work after I create the DFS call. So to be quick, let's just run the DFS call here in find words. Otherwise, we could be a little neater about it and make sure that DFS call gets the board as well. And let's just be a little neater about the code and just grab the board. Okay, and we'll call it on self.dfs just to be neat. So let's get the next. So I int j int, we're gonna get a board, which is this item here, and we're gonna get a word. Perfect. Oh, we're not gonna get words, we're just gonna get a single word. So that's just gonna be a string. What's gonna happen here is if I is less than 0, and we're gonna do this parentheses thing where or I is greater or equal to number of rows. Let's get that. M times n. M is rows. So or j is less than 0, or j is equal to n, or oh, right. We do need to get to the ith item in the word. So we do need an I in there. So let's just change this to R and C. And we do need an I. So here we go. Let's just change this. And the ith item. So if board at R and C does not equal to word at I, then we're going to return false. Otherwise, we would run DFS on the 4 different directions. So we would run self.dfs, R plus 1, and C, and we do I plus 1 to get to the next character. We're going to run return. And we're going to do a parentheses and an or statement as well. So or. So this might work in the beginning, but it's not going to work any time later. That's the, I think that's the case. So let's just give it a shot anyways, see how far we can go with this, and go with the first method. And with that, I think we are good to go with our DFS call. because we will be returning true if we get the word. So word I equals length of word, return true. I think that should go first, actually. My bad. So because we're gonna move forward, and I plus equals 1, and that's no longer gonna match. So once everything matches, let's return true. Otherwise, let's keep moving on. Return false or return that. I think that should do it. Let's run the code and see if where we mess up or not mess up. And let's get to part 2. So we forgot a comma. Yeah. And we start at 0. Let's run it. We have a syntax error. So what is the syntax error? I think it's probably the word at I. Let me figure out a way to get that clearer and easier to represent, and then I'll be back. So yes, it was the parentheses error. It was not any error with the string. So it does work, as you can see. We were able to get our words, and we can pass these test cases. As you can see, it has been accepted. But if we submit this, problem where we run this time complexity, word 4 times word length, word to the word length times the number of words, we will be unable to do this. It will take way too long. The space complexity of this right now is, let's see, we are just running through everything, and we are not actually creating anything new. So it's O of 1, space-time complexity. So space is O of 1. This is the first solution that we have. And I'm for sure that this does not work. This is going to give us a time limit exceeded because it does not do the optimizations that are needed to resolve the issue that I proposed earlier. And now we're just waiting for it to, as you can see, we have reached a time limit exceeded when we are looking at these types of issues right here, where we are forced to use a trinode to solve this problem. And now that the video is 23 minutes long, I will come back with a part 2 that uses a trinode, and that will be linked in the description below. If you have anything to share about this part of the problem, you can comment below. Otherwise, wait, give me a moment. Give me one moment. Did I do backtracking here? I did not do backtracking. Give me. Let me just get the backtracking done here, and maybe that will speed things up a little bit. I think this was the output where the backtracking was not implemented, and I messed that up. So let's get backtracking working. So we need a visited node. So we'll have to add that. This is the problem with separating this stuff out, is that we don't get to keep all our information in find words. But then it does make things a little bit clearer about like how to read the code. But yeah, it's quite something when we have like this whole shenanigans of the shenanigans that I'm talking about is that this huge long I think argument section for the function. So visited dot add RC. So this way we don't return to the same placement as before. Found equals, there we go, and then visited dot remove R and C. Let me check if that's how it's done. Okay, hello there again. I have made a lot of changes and it is accepted now. The reason why that we had an error earlier was because our output was longer than our expected output, and so we used the set instead, so that we only added once because we probably found OA multiple times, and that's what occurred, because we found OA here and OA down this way. So to help ourselves resolve that issue, we used a set instead, to find the words. Also, even though we found it multiple times, we would be fine. We also added the backtracking like we promised, but this required us to use another argument for our function, and this function has gone really long. But it does the job, and let's run all the example test cases as well. So it does work, but I think it is a bit cumbersome at this point, and I don't know if separating this out is helping us or just not doing anything for us. Let's just return here. With that, we're able to complete half the problem, and let's submit and get the wrong answer like we suspect. There should be a time limit exceeded because this is inefficient on the average case and will not be accepted by lead code. But I don't know if you can come up with we can come up with a better type of, problem within 25-30 minutes, because the try node is going to be taxing. So let's move on to part 2 of this problem and find out how we can do this problem more efficiently. And you can find that in the link in the description below. I'll see you in the next one. Thank you. Bye.